This is the video lecture for section 4.1, which is entitled Probability Distribution Function for a Discrete Random Variable. In this section, we're going to be picking up two important definitions. Both of them have subtle parts to them, and so we're going to look at multiple examples that correspond to each definition so that we can make the ideas more concrete. The first term we need to define is random variable. A random variable takes on a unique numerical value for each outcome in the sample space of a probability experiment. Part of this definition is pretty straightforward. Because we called it a random variable, it makes sense that the variable's value is determined by chance, and that's what the last part of the definition says. The value it takes on comes from some outcome in the sample space of a probability experiment, so it's determined at random, hence the name. The part that's subtle is that we require that that variable take on a numerical value, and furthermore, we have this extra condition that it takes on a unique numerical value for each outcome in the sample space of a probability experiment. For those of you that remember your algebra, this is similar to how we require that each input to a function correspond to a single output. You can't have multiple outputs for the same input. Let's look at a classic example. Our experiment is that we're going to roll two dice, and in the lower right-hand corner down here, I've got the familiar sample space with the 36 possible pairs of dice. What would constitute a random variable for this experiment? Well, I guess there are a few options, but the most obvious one is to just add up the top faces, find the sum of the top faces when you're done rolling. That's what you usually do with dice when you play dice games, is you add them up. Not always, I know, but that is probably the most common thing to be done with dice. So you can see that this variable is going to be determined by chance because we're rolling the dice, randomizing the outcomes. So there's the random part. You can see that it's going to be a numerical value because the answer is going to be a sum, so we get a number out of this. The uniqueness comes from the fact that when you add two numbers together, there's only one result that you get. So for example, if we were to get this outcome where the red die is a 3 and the white die is a 5, there's only one sum that's associated with 3 and 5, and that's 8. That's the unique numerical value associated with that outcome. You can't get a different sum from that because there's only one result when you add 3 plus 5. We've got a unique numerical value that's determined by chance, and that's a random variable. Here's a second example. One of the more popular multi-state lotteries is called Powerball. So in this example, our experiment is to be playing one $2 Powerball ticket for a $100 million grand prize. So you're going to get a ticket with 6 numbers on it. You get 5 regular numbers and then one extra number called a Powerball. So 6 total numbers on your ticket. You can choose those. You can have those randomized by the computer. And then based on how your ticket compares with the balls that are actually selected, there's a unique prize associated with that. So I put the table in the lower right-hand corner. In order to win the grand prize, you have to match all 5 of your regular numbers plus match the Powerball. Anybody who does that gets the grand prize. You'll notice that the odds are really against you there. They're about 1 in 292 million. But there's one unique outcome associated with that. In this case, it'd be $100 million. If you only match the Powerball down at the bottom, there's a unique prize associated with that, $4. So each ticket is associated with exactly one numerical outcome. And there's one outcome that isn't given in the table. I mentioned it down here. Most of the time, you're going to lose when you buy a lottery ticket. In this specific setup, you lose 96% of the time. 96% of the time, the outcome associated with your ticket will be a loss of $2, which we could represent by -2 as the value of our variable. And so our variable, the amount of money won or lost, is determined by chance because the numbers are coming out randomly. And for each possible ticket, there's one amount of money associated with that, whether that's a profit because you match one of these, or whether you have one of the 96% of the possible tickets that are losers, in which case a random variable would take on a negative value. So one more time, a random variable takes on a unique numerical value for each outcome in the sample space of a probability experiment. Now these two examples happen to be discrete random variables because there are gaps between the possible values of the variable that you take on. In fact, there are only a finite number of possibilities altogether. And so these are discrete random variables. We can also talk about continuous random variables, and that's something we'll cover after Chapter 4. In this chapter, we're going to focus on discrete random variables. One thing we often want to do is look at the pattern of variability for all possible outcomes of that discrete random variable, and that's what we call a discrete probability distribution. A discrete probability distribution is a table, graph, or mathematical rule which pairs each possible value of the random variable with its corresponding probability. So we looked at something similar when we were talking about graphs. We looked at frequency tables. A frequency table paired classes of values of the variable with their corresponding frequencies. A probability distribution is similar in that it pairs outcomes of a probability experiment with corresponding probabilities. In the discrete case, when there are a small number of possible values, we can make a table, and that's what we're going to do in this section. In more complicated cases, we might prefer to use a graph or a mathematical rule. And the graphs or mathematical rules will be something we definitely have to rely on when we move on to continuous random variables in the future. Here we're focusing on the discrete case. And again, what we want to accomplish here is to find the pattern of variability of the random variable by making a table and looking at how each value of the variable corresponds to its probability. Let's create a few discrete probability distribution tables based on some examples. Our first example, our experiment is to flip a coin 2 times. So the sample space associated with that, let's see, what are all of the possibilities? We could get heads on the first flip and heads on the second flip. We could get heads first and tails second. We could get tails first and heads second, or we could get tails both times. 4 possible outcomes of this experiment. Now, those outcomes, heads then heads, can't be the values of a random variable because those aren't numerical. We have to find something to count up. And so I've chosen as our random variable the number of tails. By making the random variable the number of tails, I've assigned a unique numerical value to each possible outcome of this experiment. The first outcome, heads heads, would be associated with the value x equals 0 because it has 0 tails. The second outcome would be associated with x equals 1 because it has 1 tail. The third outcome is also associated with x equals 1 because it has 1 tail. And the last one is associated with x equals 2 because it has 2 tails. So what I want to do is turn this into a probability distribution table. And I'm going to make my table vertically. And you can kind of see I called the value of the random variable x, which is very common. And then to the right of that, I don't want to put a frequency, I want to put a probability. So I'm going to put the probability that the random variable takes on the value x. Let's go back to the definition. A discrete probability distribution is a table, graph, or mathematical rule which pairs each possible value of the random variable with its corresponding probability. So on the left side, I'm only going to list the possible values of the random variable. That is, values of the random variable that have a probability other than 0. So what are the possible values of the random variable? Well, you can get 0 tails, you can get 1 tail, you can get 2 tails. We don't need to list values of the variable that aren't possible. Like I'm not going to write 3 down here because getting 3 tails is impossible. It has probability 0. You can safely assume that any number that hasn't been listed has probability 0. We only list the possible values of the random variable. And then to the right of that, we're not going to put the frequencies, we're going to put the corresponding probabilities. There are 4 total outcomes, so if we agree not to reduce, each of these probabilities will have denominator 4. There's only one outcome in the sample space that's associated with the value x equals 0, so x equals 0 has a probability of 1/4. There are 2 outcomes with 1 tail, and so that probability is 2/4 or 1/2. Again, I don't care if you reduce, and there's a reason why I'm not reducing here. And then the last possible value of the variable is 2, and there's 1 outcome associated with that. This table represents a probability distribution for a discrete random variable. It's what we call a discrete probability distribution. It pairs each possible value of the random variable with its probability. From this table, we get an idea of the pattern of variability of this random variable. We can see that the most likely outcome is that you'll get exactly one tail because it has the largest probability. We can see that the distribution is symmetric because it goes up by 1/4 and then down by 1/4 right back to the same level. So there are all these things that we can see in the table. One thing that should always happen in your probability distribution is that the sum of the second column should always be exactly 1 or 100%, depending on how you're representing your probabilities. So if we were to take the sum of the probability column, we should get 1. Let's see, 1/4 plus 2/4 plus 1/4. And now you see why I didn't bother to reduce, because I wanted to add these fractions together. That's 4/4, which really is 1. The only reason you shouldn't get exactly 1 or 100% is if you've got rounding issues. So for example, if you created a probability distribution where you've got decimals for your probabilities and you had to round a couple of them, maybe the column won't add up to exactly 1, but it should be close. Let's do another one with one of our favorite experiments. We'll go back to rolling 2 dice. The random variable will be the sum of the top faces. I'm going to make a table that pairs all of the possible outcomes, which we'll call x, with their corresponding probabilities, which we'll call p of x. The smallest possible sum that you can get is 2 when you roll a 1 and a 1. And the largest possible sum you can get is 12 when you roll a 6 and a 6. And you can get every integer in between those. So I need to list all of the integers from 2 to 12. And then next to that, I need to list their corresponding probabilities. And again, I'm not going to reduce any of these fractions because I'm going to add to make sure that I have everything covered. So there's only one way to get a sum of 2, and there are 36 total possibilities. So the probability associated with the outcome 2 is 1/36. There are 2 ways to roll a 3. You can see it down this diagonal right here. So that's 2/36. And there are 3 ways to roll a 4 down this diagonal here. So that's 3/36. And it continues to increase by 1. So for example, that last one that I wrote in there, 5/36, that comes from this diagonal right here. There are 1, 2, 3, 4, 5. And then there are 6 different ways to roll a sum of 7. And you can see that's the longest diagonal on here. So when we go to the next one, 8, it will drop back down to 5 possibilities. And I'm not going to make you watch me count them all out. I promise you it goes back down 4, 3, 2, and then 1/36 for the last one. And that's our probability distribution. Real quick check here, I'm just going to add this mentally. We're not going to write it out. We're also just going to add the numerators. 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, plus 5 is 15, plus 6 is 21, plus 5 is 26, plus 4 is 30, plus 3 is 33, plus 2 is 35, plus 1 is 36. That'd be 36 out of 36. Which I guess doesn't guarantee that we're right, but if it didn't add up to 36 over 36, we're definitely wrong. For you game players out there, you gamblers, this is an important probability distribution to know. This is something that I use on a regular basis with all the nerd games that I play. Let's look at one more example, and this one's going to be a little more practical, a little more like real life scenarios, although it is simplified just so that we don't have to deal with a monstrous probability distribution. Here's the scenario. An insurance company sells a 1-year policy to a person in good health for $250. Based on the person's age, the company assumes that there is a 99.6% chance the policyholder will survive the entire year, but in the event of their death, the company will pay $100,000 to the family of the customer. So from the perspective of the insurance company, this is a risk, this is a gamble. They're taking a small amount of money under the assumption that the person will survive, but in the unfortunate event of the death of this person, they're going to have to make a massive payout to the family. So it's almost like the insurance company is gambling. This is essentially what they do, and they base their rates on these probabilities. They look at things like mortality rates and so on. This is one of the reasons why statistics and probability were invented in the first place. So to make this clear, I've declared the random variable to be the profit or loss for the company rather than from the customer's perspective. So we're going to make a table here, and I apologize, it's going to be kind of small. But we don't need a whole lot of space because there are really only two outcomes. The person either lives or they die, and for each of those outcomes, there's a unique numerical value associated with that. If the person lives, then the insurance company just gets to keep the $250 and they profit. Again, we've simplified this because there are other costs that go into selling this, like they have to pay the employees to the company and so on. That's where the simplification comes in. This isn't exactly lifelike. But we'll just call this $250 of profit from the company's perspective. And the other possibility is that the person dies. And if the person dies, they're going to make a $100,000 payout to the family. But remember, they took $250 up front, so they don't lose the full $100,000. They lose the difference in those, which is $99,750. And because it's a loss from the company's perspective, we want to make sure to represent that by a negative number. If we put a positive number there, it's going to come off like it's a gain. So a negative number will indicate a loss here. So there are two numerical outcomes to this experiment. A gain of $250, they make $250, or a loss of $99,750 due to the big payout to the family. Now we just have to pair each of these with their associated probabilities. The probability that the person lives is 99.6%. And remember, we're going to pair that probability with a 250 because that's the outcome when he lives. They gain $250. I'm going to convert that to a decimal and write 0.996. There's nothing wrong with writing it as a percent. You could also turn it into a fraction if you wanted to. You'll notice that we weren't given the probability that the person dies, right? That's not given anywhere in the problem. But we can deduce it, and we can think of it in two ways. Thinking back to the previous chapter, these are complementary events. He either lives or he dies. And so the probability that he dies is 1 minus the probability that he lives. That's the complement rule. Or thinking about what we said for discrete probability tables, this column needs to add up to 1. And so the number that we put for probability here has to be a number such that when we add it to 0.996, we get 1. And how would you get that? Well, you would subtract from 1. Either way you think of it, we need to subtract 0.996 from 1. That's 0.004. And that's our other probability. This is a discrete probability distribution because it represents all of the possible outcomes for a discrete random variable. As long as you've got a small number of outcomes, this is an effective way to show a probability distribution. When we get into more complicated experiments with more outcomes, or when we move on to continuous random variables, these tables won't cut it. We'll have to go on to something else. We'll be focusing on the mathematical rules, what we call probability distribution functions. But when the number of possible outputs is small, a table is a great way to display this information. We'll be using this technique in the next section to find what we call expected values, which is a natural follow-up to this section. But we're getting ahead of ourselves. Make sure you focus on these two definitions, and if you have any questions, let me know.